Hey everybody, we are in chapter 10 and we're looking at inscribed angles. So let's take a look at some of the vocabulary associated with it. Well, obviously the first vocabulary word we need to talk about is what is an inscribed angle. So I'm going to draw a circle like that. Okay, I know it looks bad, but just trust me, it's a circle. And I'm going to draw what is an inscribed angle. So an inscribed angle is an angle that has its vertex, that's a little elbow joint or corner point, on the edge of the circle, and the rest and its rays pass through the circle. So that's not an inscribed angle. That's not, because the rays are not inside the circle. But here, the rays of the circle, at least part of them, will be going through the circle. The textbook might have a different definition, but the idea is the same. So this is an inscribed angle. Let me highlight it so we have that vocabulary word. Boom, chicka. All right, now that we have that, we need to figure out what the intercepted arc is. And the intercepted arc is going to be the arc that is intercepted, right? So this would be the intercepted arc. And so there's a relationship that we're going to explore in the textbook. If this angle here is, oh, let's use a pen. Sorry about that, chablitos. If this angle here is x degrees, right? This arc measure, which we know comes from directly from the central angle here, this arc measure will be twice that. Therefore, the central angle is also twice that. So that's the big story. And we'll get to that in the lesson. So if it doesn't quite make sense, we'll get there. But let's check out our lesson, see what things our lesson has for us. So here we are with theorem 10.6. And what we're talking about is the inscribed angle theorem, what I was alluding to earlier. If an angle is inscribed in a circle, boom, boom, and then the measure of the angle equals half the measure of the intercepted arc. So this angle is going to be half this intercepted arc. So whatever this intercepted arc is, you're going to take that and cut it in half. And that also backtracks and it goes for the central angle. Because we remember that the central angle is the same size as the intercepted arc. The central angle has the same measure as the intercepted arc, but the inscribed angle is going to be half of that, all right? All right, so let's see if we can use that to help us with example 1. Here we are, example 1. We've got a couple of inscribed angles and we have some information. The first thing they ask us is to find the measure of angle P. Angle P is out here, but we know the measure of the intercepted arc is 70 degrees. We remember that the intercepted arc is equal to 2 times the measure of the inscribed angle. And so with that in mind, we see the relationship between P and the relationship between MN, arc MN, has to be 1/2. And therefore, I know you probably got it a long time ago, this angle here is going to be half of 70 degrees, which is 35 degrees. I hope that makes sense. And then over here, we have that the arc PO is going to be twice this intercepted or this inscribed angle. Is this making sense? This arc here is twice this because this is half of that. All right, so I'm just going to double that 56 degrees and I get 56 times 2, which is going to give me 112 degrees. That looks really shady. Let's try it again, which is going to give me 112 degrees. All right, so the first one is 35 degrees and the next one is 120. And here we have theorem 10.7. In words, the theorem reads, if 2 inscribed angles of a circle intercept the same arc or congruent arcs, then we know that those angles are congruent. Totally makes sense. So let's look at the picture. The picture has us here. Let me use my highlighter. The picture has us here considering this arc AD. And if you notice, angles ACD and angle ABD are both intersecting that same arc. What this picture tells us and what this theorem really tells us is that these 2 angles have to be equal. Not too bad. So we're going to use that fact to answer example 2. So here in example 2, we have an arc that's being intersected by 2 inscribed angles. And from that theorem, we know directly that whatever this arc measure is, these guys are going to be half of it, but also these guys are equal to each other. So I'm going to start off with the premise that angle STV is equivalent to angle SUV. Therefore, 3x minus 5 has to equal 2x plus 15. And then we have some run-of-the-mill regular old algebra here to work on. And when I do that, I get not 2x, my bad, Chablitos. It's so easy, I got it wrong, right? X minus 5 is equal to 15. Now I'm going to move the 5 over to the other side, so I get x is equal to 20. That's not the answer, right? Because they asked us to find the measure of angle t. So I need to take that 20, plug it into for the x value, and then calculate. So then I end up with 60 minus 5, which is 55 degrees. So let me put a finer point on it. The measure of angle t is equal to 55 degrees. Oh no, just when you thought we were over two-column proofs, they rear their beautiful yet challenging heads again. Here we are. We've got example 3, and we're going to use inscribed angles in a particular proof. Let's take a look at our picture and what's going on. They give us that JM is congruent to KL. Arc JM, so I'm going to actually highlight that or write over it. JM, this arc right here, is congruent to this arc right here, KL. All right, you remember our theorem just told us about the intersection of congruent arcs with inscribed angles give us equal angles. Golly, that's a mouthful. So as soon as I get that, I'm starting to look around and say, okay, what angles do I know must be congruent? But we'll get there later. Then we've got to prove that triangle JMN and triangle KLN are congruent. So the two triangles that we're trying to prove congruent would be these two that I've highlighted in red. So let's talk about how do we find triangles congruent. Remember back in the day, your thoughts should be around the idea, that's you by the way, you child, you're thinking. How do we consider triangles? How can we prove that triangles are congruent? You might remember, oh yes, we've got angle, side, angle, and side, 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 and side, angle, side, and some other ones, right, depending on the type of triangle we have and what other information. So right now what I'm noticing is that we do not have a whole lot of information about sides. We definitely can talk about angles. Let's say we can prove easily that these two angles are congruent because they're what? I can't hear you. What? Vertical angles. Good. Awesome. Yes, they are vertical angles. Yes, and the baby agrees too. We can also, can we talk about any other angles? Can we use maybe this theorem to talk about some angles? And after we get an angle, we have to at least get a side because none of these angle, angle, angle isn't a theorem, but angle, side angle is, or side angle, side. Can we find out any information about sides? That's what you should be thinking about right now. Okay, so I've left you alone long enough to consider how you're going to approach the problem. And I know what you saw. You were like, well, what about this arc over here? And I said, yes, I understand. We have an arc here. And you said the theorem that we're talking about actually talks about two angles intersecting the same arc. Two inscribed angles intercepting the same arc means that we've got two equal angles there with those. And I said, yes, I agree. And then you brought my attention over here to JK, and you said, well, clearly these angles here must be equivalent by the same logical reasoning. So then you said we've got angle, angle, angle. And I say, no, we can't have angle, angle, angle because that's not a thing. So we need to find something about a side. Does anybody see anything? Anybody? You in the back, what do you think? I can't hear them. What I hope they're saying is this. The arc JM being equivalent to arc KL gives us not an angle that's equivalent because there's no angles that really branch off from that are intercepted arcs, right? What we do get is that segment KL and segment JM, this is from the last section, when you have two arcs that are equivalent, that have the same corresponding chords. I'm not sure what the language was, but have chords. Then those chords associated with those arcs within the circle that are congruent. I know I'm saying a lot of words, but the fact that these two arcs are congruent and these chords are the chords associated with those congruent arcs, that means that those chords are equal. So now we're going to prove this thing true by angle, side, angle. Are you guys impressed? I'm kind of impressed. Angle, side, angle. All right. So here's what we're going to do. We'll start off our proof by writing down our given information. So here we have it. Our only given statement is right there. What can we get from our given statement? The fact that these two arcs are equivalent. We got that JM is congruent to KL. And that this reasoning comes back from theorem 10.2, which tells us that if we have in the same circle or in congruent circles, two minor arcs are congruent if and only if their chords are congruent. Their corresponding chords are congruent, right? So I write this as my reasoning. Minor arcs are congruent if and only if corresponding chords congruent. And if and only if means it goes either way, right? So if I start off with the chords, I can end up with the arcs. If I start off with the arcs, I can end up with the chords. And now our next bit of information is going to talk about these angles. If you take a look, LJ M is congruent to MKL because why? Because they intersect the same arc, right? They intersect the same arc. And then the same thing with angle JMK and angle KLJ. Those two angles that I've marked in green are congruent because they intersect this, the same arc. All right, so there's our logic there from that last one. If two inscribed angles intercept the same arc, then the angles are congruent. So let's take a little bit of an inventory. We're trying to prove these two triangles are congruent. We've got two angles congruent. We've got a side congruent. I think we've got it. We can say that triangle JMN is congruent to triangle KLN, and we can say that because of these three bits of information here. Well, this information and these 2 points that I shoved in point 3, we can say that the two triangles are congruent by angle side angle. If you look at this angle here in example 4, angle G, right? We see that angle G is an inscribed angle. We know that this is the diameter. This arc is a semicircle, so we know that the measure of this arc is 180 degrees. The measure of this angle is 90. Are you guys with me? So this is a right angle triangle. If this is a right angle triangle, we know that the other two angles in the triangle are going to be complementary, meaning they add up to 90 as well. So that tells me how to find F pretty easily. I'm going to take these two angles, add 4x plus 2, then add to that 9x minus 3, and I recognize that that's going to be 90 degrees. With some algebra, I'm going to join some like terms here. Minus 1 is equal to 90. Then I get 13x is equal to 91. X, I believe, is equal to 7. With x being equal to 7, we now can find F by simply substituting in 7 for the value of F, right? For the value of x in F. We'll get there. So 4 times 7 is 28 plus 2 is 30. We can say that this is a 30-degree angle. So here we have this cool theorem that tells us if we have a quadrilateral that is inscribed within a circle, something happens. The opposite angles are going to be supplementary. We don't remember what supplementary means. It means that those angles add up to 180 degrees. So this angle over here, angle L, will be supplementary, not equivalent, but supplementary to angle N. So these two added together would be 180, and these two added together are 180. So here in this real world example, we have a charm that is on a necklace that's inscribed in a circle, and so we know from our last theorem that this angle here will be supplementary to this angle here. And they're not equivalent, they're supplementary, which means when I add them up, I'm going to get 180. And the same thing with these two angles. These guys are supplementary as well, right? But not only are they supplementary, because they add up to 180 and this one's 90, you already know this one's 90. So I'm just going to go ahead and put that information down. The measure of angle A is 90 degrees. But to calculate B, we've got to add up these two angles and set those two equal to 180. With a little bit of algebraic manipulation, we get that 3x, add the 30 to both sides, we get 210. 210, x is equal to 70. Since x is equal to 70 and b, angle B is supplementary to it, we know clearly that angle B must be 110 degrees. With that in mind, my friends, I'm out.